Hello everyone, and in this video we're going to be talking about problem A1 from the 2014 USA Physics Olympiad. And this problem centers around a unicycle moving in a circle. And our problem says a unicyclist of total height h goes around a circular track of radius r while leaning inward at an angle theta to the vertical. The acceleration due to gravity is g. And so the problem is broken into two parts. First part allows you to assume that h is much less than r, and it asks what angular velocity omega must the unicyclist sustain. So here we have a diagram of the situation, and as you can see, we have represented the unicyclist as a uniform rod. And so for this problem, if we worked in the ground frame, then we would have a rotating angular momentum vector, and that would be a bit more difficult to deal with. So the easiest way to do this problem is to work in the rotating frame of the unicyclist so that the problem becomes a statics problem instead of a dynamics problem. So now that we've switched to this rotating frame of reference, we can start by drawing a free body diagram of the situation. So obviously we have the force of gravity acting at the center of mass of the unicyclist, and we also have a normal force pointing up from the ground and a friction force from the ground as well. But since we're working in a rotating frame of reference, we actually have to account for the centrifugal force as well, which is a fictitious force. And this is where the approximation h is much less than r comes in, because if you recall, the centrifugal force on a mass m is going to be mr omega squared. But since the unicyclist is leaning inward, then not every part of the unicyclist's body is going to be at the same radial distance from the center of the track. And that means that the force per unit mass, which we can consider to be similar to, in principle, to a gravitational field, is going to be non-uniform over the body of the unicyclist. But in this case, since the span of the unicyclist is going to be much less than the radial distance, then we can assume that the value r omega squared basically doesn't change that much over the body of the unicyclist. So the force per unit mass is going to be uniform across, or approximately uniform across the body of the unicyclist. And so that means that similar to a gravitational force, where we have a uniform force per unit mass, we can assume that the centrifugal force can be replaced by a single force acting at the center of mass of the unicyclist. So this completes our free body diagram. Now, in order to find an equation relating the angular velocity to other known quantities in this problem, we need to either balance forces, balance torques, or both. So if we were to just balance forces, then horizontally we can say that the centrifugal force has to balance the frictional force, but we don't know what the friction force is, so that's not going to be very easy to do. And vertically, that just tells us that the normal force is equal to mg, and that also doesn't tell us much. So it seems that we have to balance torques in order to get a meaningful equation. So when balancing torque, we have to be careful with what origin we choose to calculate torques around. And here, the most convenient origin would be the point of contact with the ground, because that eliminates the torque due to the normal force and the frictional force, since they both have zero moment arm about that point. So if we choose that origin, then the torques from the normal force and the friction force simply vanish, and we just have to deal with the torque from gravity and the centrifugal force. So how do we do this? Well, we need to calculate the torque, since these two forces, gravity is going to try to cause a counterclockwise rotation about this origin, whereas the centrifugal force wants to cause a clockwise rotation about this origin. So these torques are in opposite directions, but if they're going to balance, then they have to have equal magnitude. So we have to calculate the magnitude of the torque from these two forces and then equate them. So to do this, we need to find the moment arm of each force. And note that we can draw a right triangle here where the angle theta is given to us, and it's the angle that the unicyclist makes with the vertical. And this tells us that these two values, these two side lanes, the opposite side is going to be h over 2 sine theta, and the adjacent side is going to be h over 2 cosine theta from some basic trigonometry. So now we can calculate the torque from the centrifugal force as Fc times its moment arm, which in this case is going to be h over 2 cosine theta. And we can calculate the torque from gravity, which is going to be the force mg times its moment arm, which is h over 2 sine theta. So this gives us an equation to work with. But we also need to replace Fc with the expression for the centrifugal force, which is just going to be mr omega squared, since we're going to assume that it's uniform across the entire body of the unicyclist under the assumption that h is much less than r. And now we can cancel out the common factor on both sides. So we're just left with r omega squared cosine theta equals g sine theta. And if we rearrange this, we get omega squared is equal to g sine theta over r cosine theta. And since sine theta over cosine theta is tangent theta, this gives us g over r tangent theta. And square rooting both sides, we get the answer omega equals square root of g over r tangent theta. So now we can consider part B of the problem. The problem now says model the unicyclist as a uniform rod of length h, where h is less than r but not negligible. This refined model introduces a correction to the previous result. What is the new expression for the angular velocity omega? Assume that a rod remains in a plane formed by the vertical and radial directions, and that r is measured from the center of the circle to the point of contact at the ground. So now we have to alter our diagram so that h is not negligible compared to r. But the difference here is that whereas before we can assume that the force per unit mass by the centrifugal force is, which is equal to r omega squared, is going to be uniform over the entire body of the rod. And that allows us to assume that that force acts effectively at the center of mass of the rod when we calculate torques. And this is similar to gravitational fields, because recall that a gravitational force is equal to mg. And if we have a uniform gravitational field, then that means the force per unit mass due to the gravitational force is going to be uniform at any point on an object, since it's just equal to g and it points in the same direction. So if you do the calculation, you can find that in that case, the center of gravity, or basically the point at which we can replace the entire gravitational force with a single force, and it will give us the same calculation for torque, is precisely located at the center of mass. But if we have a non-uniform gravitational field, so that the force per unit mass is not uniform, not the same over the entire body of an object, then we can't say that the center of gravity, or where the force of gravity effectively acts for the purposes of calculating torque, is at the center of mass, and it'll be at a different point. And this is precisely what's going on here, because we can think of the centrifugal force as basically the same as a gravitational field, except the field we're concerned with is r omega squared, and that's equal to the force per unit mass due to the centrifugal force. So in this case, r is going to vary significantly between the two ends of the rod, and that means that we cannot assume that this is like a uniform force per unit mass over the entire body of the rod. So in order to calculate the torque now, we have to consider each tiny piece of the rod separately, since they're all at different radii. And so here's an illustration of that. You can see that the effective, I guess, centrifugal field, if you want to call it that, is proportional to the radial distance, and it's going to be pointing radially outward, which is the direction of the centrifugal force. And so you can see that these arrows, which represent the centrifugal field at each point, is not going to be uniform over the entire body. And that's what causes, I guess, the center of the centrifugal force, the effective point at which it acts, is not going to be at the center of mass anymore. And so we have to calculate the torque by integrating over the entire length of the rod, instead of just placing a force at the center of mass. So to do this, we can break up the rod into a bunch of infinitesimal pieces. And here, one of those pieces is shown. And we can call the distance from the bottom of the rod to that point at that location of that segment to be S. And so the length of the segment, length of that small piece is just going to be ds. Now, in order to calculate the centrifugal torque on that certain piece, we're going to have to find, first of all, the centrifugal force on that piece. And since the centrifugal force is proportional to r omega squared, we're going to need to know the radial distance. So how do we find a radial distance? Well, we can draw a right triangle around the segment that is below this infinitesimal piece. And we know that the problem gives us the angles theta to the vertical. So using some trigonometry, we know the opposite side is s sine theta and the adjacent side is s cosine theta. And since the total radius of the circle is going to be r, and we have a horizontal distance s sine theta inward, then we can say that the radial distance of the infinitesimal piece we're considering is going to be r minus s sine theta. Now, in order to calculate the centrifugal force on this piece, we also need to know its mass, since the centrifugal force is mr omega squared. So we can call that small infinitesimal mass dm. And that's just gonna, since it's a uniform rod, that's just gonna be the mass density of the rod, which is gonna be m over h times the length of that infinitesimal piece, which is ds. So now we basically have everything we need to calculate the centrifugal force on this piece and the infinitesimal centrifugal torque on this piece. So you can see here we've drawn in the infinitesimal centrifugal force on this piece on the diagram. And that shows us that the moment arm of this infinitesimal force is going to be this adjacent side s cosine theta. So what is the torque? Well, the torque is just going to be equal to the force times the moment arm, which is dfc times s cosine theta. So we just need to replace dfc in this equation. And that's going to be equal to dm, the mass of the segment, times r omega squared. And since we know r is equal to big R minus s sine theta, we can replace that. And we also know dm is m over h times ds, so we can also replace that. And if we rearrange this a bit, because we're going to be integrating this expression over all values of s, we can write this as m omega squared cosine theta over h outside of the parentheses and inside the parentheses rs minus s squared sine theta all times ds. And since s is the only variable here and sine theta is going to be a constant, the expression inside the parentheses is basically just a polynomial. And we can, once we integrate this expression here, we're just integrating this from 0 to h, since that's the value of s at the two endpoints. The expression, we can just use the power rule to get the integral. And once we do that, we get inside the parentheses rs squared over 2 minus s cubed over 3 times sine theta. And we're evaluating this from 0 to h at s equals 0. The parentheses gives us a value of 0, whereas at h, it gives us rh squared over 2 minus h cubed over 3 sine theta. So this is just equal to that value, since we're subtracting out 0. Now, this is a good expression for the torque, the total torque about the point of contact with the ground due to the centrifugal force. But we need to balance the torque against the torque due to gravity using basically the same process as in part A. And luckily, the gravitational field is still going to be assumed to be constant over the entire body of the unicyclist. And that means that we can still basically just assume that the center of gravity, the point, basically the equivalent point where we can replace the force of gravity with a single force, is going to still be at the center of mass. So the torque due to gravity is still going to be just mg times h over 2 sine theta as it was in part A. And if we equate these two expressions, then first of all, we cancel out the common factor of m and h. And then if we just rearrange the equation, then we're going to get omega squared equals square root of g over r tangent theta, and then divided by 1 minus 2/3 h over r sine theta. And we write it in this form because the first part of it, the square root of g over r tangent theta, is just the answer to part A, and then the second part represents the correction to that result. And you can see that if we take h to 0, which is basically the approximation in part A, then the second corrected term just equals 1, and we just get the same answer as part A. So that is the answer to part B of this problem.